about this slide, so this building seems to have become very important because Professor Penning also showed it, and I also showed it in the first presentation. And the question we were asking is that is this acceptable for the people who lived there and who had to leave more than a year, 2 years, and lost all of their investment because they bought it to live there, and now it's still code compliant. And I would say if you even do performance-based design, you will find that many of the performance objectives might be met even with this code, this level of damage. So the question still remains, is this acceptable? And are people going to accept this as a good design if their whole life has been disrupted? So let's look at who are the stakeholders in making buildings like this, and especially tall buildings, and see who has the responsibility to make it better. If you look at that, you will see that we have several stakeholders. The key ones are, first of all, the building officials, whose main job is to ensure public safety. Then on the left-hand side, you will see the building codes, which are developed to ensure public safety. Then you have the designers, like us or others, who are given the task to design these buildings. We have the developers who own or develop this building, who invest the money to make it. And then we also have the contractors who do the construction. And finally, when the construction is done, this is handed over to the owners, who may be the developers, maybe somebody else, and then finally the residents. And of course, many people can be the same, can play the same role. The developer could be owning the building and they could be using for their own business. So, but right now, let's separate them into these groups. So now the question is that who should be paying for or responsible for making it better so that we don't end up seeing the buildings that we have seen? So if you just look at two main groups, one is the developer, and the second one is the buyers or the residents. Let's look at them, what are their interests are. And we actually tried to invite some of the developers to this seminar because we thought we will hear from them and also share our thoughts with them. So it's obvious that the developers do this as a business. So they make buildings as a primary business. For them, that's their business. They're interested in making profit out of that, and they should rightfully do. So anything that makes more profit would be what they would be interested in. However, they are willing to pay or spend more if they see the value and they can get better profit. So if you can convince them that if you spend more, you will get more profit, they will do that. But if you try to convince them that if you pay more or spend more and you may lose profit, it's very hard, even though it improves public safety. Just like green buildings. The developers started to pay attention to green buildings when they started to make some benefit out of that, either as a brand name or as charging more to the client or so on. Same thing can happen in engineering. On the other hand, the buyers of the public, their main concern is that they use these buildings for their living as well as for their livelihood. So for them, building is everything. They live there, they work there, or do both, or one of these. They care about livability, they care about safety, they care about comfort. And they also care about the price they pay. So the price they pay, they want to get the maximum value for their money. They would pay more if they think that they are getting a better product. Just like when we go to, like we are here, when we drink coffee here, we are willing to pay 200 baht. When we go on the street, we don't want to pay more than 15 or 20 baht or 30 baht. Because we think we're getting more value here for our coffee than over there. So if somehow we can convince people that they're getting more coffee, more coffee, more value, I think I need coffee together. So they will be convinced to pay more. So I think this is the key to this equation, that if the developers who are making the buildings, until they see a business benefit or business sense in that, they would not be willing to spend or make it better. And at the same time, if the public does not realize that they can spend more to get a better building, it will not work. In our case, in Philippines, we have been very, I would say, successful through our friend Boise. We met with many developers. Some of, you also saw the vice president from Ayala. They're one of the companies that we met, and many of them. And we talked to them, this kind of slide. And it seems that they understood, or they bought this idea, because one of the developers, he put this in his advertisement for we wrote that part, he put it in the advertisement for his building apartments, that these are designed for a better safety level than the code. And the developer, seemed to charge more for his apartments than rivals. So this became a business case. And then other developers thought, oh, this is interesting. So they also thought, let's do this. Let's go beyond the code, make a better building, and then we can charge more. And the cost of that extra cost is marginal compared to the benefit they can get. For example, you know that in Bangkok, the building price per square meter ranges anywhere from 100,000 square meter baht per square meter to 300,000 baht per square meter. Same square meter per area, people are willing to pay from 100,000 to 300,000, 3 times more, because they see value in that, whatever that value is. If the safety is a concern, then if you look at the building cost, those who are here, they would know that the building costs maybe 40,000 baht per square meter, maybe land another 10, 20, 15,000. So the net area costs maybe 50,000 baht per square meter. You add some circulation and other things that cost maybe 75,000 baht per square meter, and it sells for 150,000 baht per square meter. If the additional cost to make the building safer or better is, let's say, another 2,000 baht per square meter, but the client can charge 10,000 baht per square meter easily for that added value, they would definitely be interested, because they make an extra 8,000 baht per square meter profit on it. So basically, the idea to me is that just like the environmental green building has become popular because there's a business case for that. If we have a business case for making building better, then this would happen. And these two stakeholders can do that. So how can we increase the value so that the buyers are willing to pay more? Public gets a better building, and the developer gets high profit. Everyone wins. That's, I think, what we are trying to do, so that we can come up with a system that everyone gets what they want, and it's all good. Having said that, let's see what are the value we are talking about. Of course, the value is many things. Building value has location, has so many things, MRT, BATS, whatever. Everything has value. But let's only talk about the safety. Is that something the public will value? If the public can be educated or public knows that having a safer building overall in the long run has a better safe investment for them and also better for them, then it is a value that they are willing to pay or willing to consider. So if a safer, let me just skip a couple of slides and go right away. So what are the things that we can do to add this safety value to a building? There are several things we can do. Some of them that I want to discuss today. Number one is performance-based design, because it gives us a tool to explicitly claim or check higher value, have higher safety value, because we can demonstrate that, okay, this is better than the code. And we have seen in the morning through several presentations that the code-based design, not suitable, not appropriate, not adequate for high-rise buildings for so many reasons. So if we can demonstrate that the performance-based design is going to be better, and we can show something better, that's number one. Second one is value engineering. Because performance-based design alone, without the value, added value for the builder, for the people, will not sell. And which means that we have to see that performance-based design also is cost-conscious or is value-conscious. So we are always looking at what is the value that we're adding, both in terms of safety and also in terms of the value for resources or value for money. And most important then is that peer review, because we are talking about something which is not stipulated in the code. We're talking about something that is not ordinary. So a third person, independent third person, should look at what we are doing, so that the client and the PBD or the consultants or the people do not get together and come up with a building which is not actually safe. It must be ensured that the people who are doing this are actually getting the value they're claiming. So we need a peer review as well. So these three components together can help to deliver what we are just talking about. So ensuring, let's go over them one by one, and please tell me 10 minutes before so I can speed up. The first one is ensuring explicit safety, which is basically performance-based design. And I'm going to go a little bit fast because many people have already talked about it. But before that, let me talk about this issue. That means the definition of a tall building. It's interesting how a tall building is defined. And I take a quote from CTBUH, which is one of our supporting organization for this seminar, because I think without having them on board, a tall building seminar would not be so meaningful. If you look at that, they define tall building in three ways. The first one is relatively tall, and second one is proportion, and the third one is technology, systems and technologies. So relevance is very important. If a town has every building which is 6-story and you make it a 12-story building, it's tall, not only because it will look tall, but also because the technology in that area, the engineers, the builders, everybody is used to buildings of 6-story. So a 12-story building will become a technological sort of effort for them. So it becomes tall in terms of that. Similarly, proportions, it's only tall, it should also must be slender a little bit so that we have issues with that. And then it should use technologies that are typically not used for other buildings. So that's how we will define a tall building. How modern codes look up safety, I mentioned in the morning earlier that they just hope for the best. They give you rules and they hope that all of this will lead to a safe building and people's life will be safe, and that's just about it. And it doesn't seem to prevent other things that we have seen in several presentations, including the picture and also the many damage that Professor Penning has shown in his presentations. And modern code, as I mentioned, they have rules, very arbitrary sometimes rules, and they apply them uniformly, and that's the key. I think that is the key, that the code rules are meant to be applied or intended, or they apply uniformly everywhere, irrespective of whether we need them or not. For example, in a tall building, if there are 50 floors and the code requires that you have to provide hinges on all columns below and top on all 50 floors and all columns, it's unrealistic, because not all columns are going to develop hinges in extreme earthquake. Few of them will. Not all of them are going to go into nonlinear mode. Very few of them will. And most of them will remain elastic. Why do we need the hinge reinforcement in those locations when we know that they're never going to go inelastic? If we can prove, then we will not need that confinement or that heavy reinforcement there. Similarly, shear walls. The rules say, the code says that you have to provide confinement, let's say over the height, or check simple checks. How can we explicitly check that the strains are small enough that we don't need the confinement, and so on? So the rules that we specify in the code, first of all, we do not know what happens if you don't follow them. For example, spacing of the hoop, it says 4 inches, 100 millimeter in a column, let's say. But these were developed, if you go back to the research on small column tests, let's say 300 by 300 or 400 by 400 millimeter column, where confinement of 100 millimeter or 1 inch is very important, 4 inches is very important. But in tall buildings, the columns are a meter or meter and a half. Over there, 10 centimeter or 4 inch and 8 inch have no difference in the confinement that you're going to get, because the column is quite large. Confinement pressures will not be affected by the spacing in that range. But because the tests are not done for that sizable columns, we do not have clear recommendations. So we just follow them blindly. We don't know if we change the spacing from 4 inches to 6 inches, will it really reduce the confinement or not? Will it really make any difference to the building or not? So these questions are not answered. We just follow the rules that are specified because we do not know the impact of them explicitly. But in performance-based design, if you start using vendor models and so on, you can actually vary the spacing for a particular column. You can check whether it's going to affect the moment curvature curve or not, or the hinge properties or not, and then you can see if it's worthwhile or not. So these kind of things we can actually do in more detail. So these rules do not make much of sense at that time. So I'm going to skip. We already saw the family codes. We talked about the building code. Now let's talk about this one. The concern of the owner or the public is of course concerned with safety. The owner is concerned with many questions. Will the building collapse? Will it be damaged? Can I use the building after the earthquake? How long for the damage and so on? Many questions that we ask, and Spanning already mentioned many of them, trying to from various studies, fragility and so on. We can answer some of them. Structural engineer, on the other hand, without the advanced knowledge, does not have the answers to many of them. So, because they just simply follow the code without understanding what their impact might be, because there's no explicit way to check otherwise. So, as I mentioned, the engineers hide behind the codes. And we also talked about the shortcomings of the building, especially for tall buildings. I was just looking at a presentation from Jack Moy, I think, and he mentioned that in US, only 1% buildings are considered tall. 99% buildings are not tall. So the codes are developed for 97 or 98% of the building. They don't really care about buildings which are in one less than 1% range, which we are talking about. So actually, the codes never intend to cover those buildings in the first place. So these are the motivations for the performance-based design, that we can get explicit answers, we can do things more clearly, we can go beyond. Really? How many minutes? I just asked you. Okay, all right. Not even people. Skip. Performance-based design. So let me just mention couple of things. I really have to go fast. No, go back. Yeah. Well, one important thing that I want to mention is that before I move to something else, luckily I have 7 presentations. So if I don't finish something, I will move to the next presentation. So if I don't finish this one, I'll continue with my next presentation. So one thing very important that is coming up now is that performance-based design has always been thought of something that you only do for earthquakes. But people are realizing that the concept is pretty good. We can apply it for other loadings also. Especially now, wind. Performance-based design for wind is something that people are looking at. ART, we are doing research on this one to see if the same concepts can be used for wind, extreme wind. Even for live load, just think about it. You have live load in a room like this one today, and we design it for a certain live load, and we say, the code says use a load factor of 1.6 or 1.7. What does that mean? Can it answer the question, how many people can stand on this roof without the floor collapsing? Wouldn't it be nice that we can design the floor for 600 people explicitly as an extreme case and 300 people for service case? Then we will have a very clear answer. We can write outside this floor designed for 300 people without any crack, with vibration, without any cracking, 700 people without collapse, and then forget about all the other things which are not necessary. Because that's not interesting. The design level is not interesting. The 1.7 times the live load is not interesting because it doesn't give us any information. What does that mean? But if we have explicit evaluation, then it will be, then we can link performance with hazard, no matter what the hazard is. It could be just as simple as live load. It could be wind. It could be earthquake. So explicit performance is what we are looking at. We are looking at service level and the collapse level, 2 extreme cases. In between is arbitrary. The strain limits, 0.003, never ever happens. You can ask people who are working on PVD or looking at the strains, it never reaches there. But that's the strain that we use in the design because it's an artificial created case. So we explicitly check service level for a certain hazard level, and we explicitly check collapse level, and then in between should be okay. Of course, we can have the limit states, but basically we want the thing to be serviceable, and we want it to be not collapsed or not damaged. I don't mean collapse, I mean damage. So damage level should be explicit. And owner and engineers can sit together and decide what do they want for this building to be, how important it is, how much money they can spend, what they are the owners, how much they can charge for that, and so on and so forth. And naturally, as I mentioned, a peer reviewer to make sure that they don't make a deal which is not acceptable to the public. So an independent person, third person should come and say, oh, okay, what you're doing seems to make sense. So if we have this mechanism of the owners or the developers sitting down with engineers, coming up with the performance criteria and design objectives, and a third person outside that group checks it, then it should be something that can be done to give the public a better and high performance building. So typical review, let me know when we are completely out of time. So typical review objectives we have is enhancement of performance and cost effectiveness. So both need to go hand in hand. So in terms of performance, we have indicators. We can have many things that we can study, or we can evaluate, for example, dynamic response, lateral load response, vertical load response, demand capacity ratios, the response irregularity, discontinuity. We had a very good presentation on that in the morning. Explicit performance evaluation, service, design level, or MCE. On the cost side, we can see the capacity utilization ratio. See, one of the things that you will notice is that most of your designers that we take, most of this structure is actually underutilized. Because when we design something, we take a couple of critical members. If we have 100 columns in the building, we design 4 columns and then apply them, typical column, to 20 locations. And those 4 locations which are designed are actually repeated 20 times. Other 20 locations may not be as critical as the typical column. So the utilization ratio in those locations will be very low. Similarly, we design the beams or a column or some for a certain section, and we optimize, and then the rest of the column is actually underutilized. So most part of the structure is underutilized in terms of the capacity, and few locations control that. So if you can check that, then the cost effectiveness can be checked. Reinforcement volume ratios is a typical indicator. Complete strength and quantity, rebar quantity, constructability, time, and so on. So we can look at all of these aspects while we're doing the performance evaluation to make sure that whatever decisions we're making on the performance side are also good on the value or on the cost effectiveness side. Performance objectives we have seen in the morning, so I can skip that slide also. Ground motion, we have talked a lot about that. Response spectrum, we have talked a lot about that. We have also seen the typical acceptance performance criteria from operational to collapse prevention and anything in between. So basically, depending upon the use of the building, the type of hazard, the type of consequences, we can define where the building is going to be for various hazard levels. The performance can be checked at many levels. It can be checked at global level. It can be checked at local level. Because ultimately engineers need some numbers. You know, we all like numbers. So we want to know, okay, what does performance immediate occupancy mean for me? It means for you that your rotation in this beam should not be more than this one. Then the engineer is happy, because now he has one number, or she has a number to check. And if you say, okay, your ductility ratio must be like this at the column location, or a wall, or a strain limit in the rebar, in the shear wall should be like this, and they can check it, then it's fine, they can check it and move on, and then we can accumulate that information into performance objective compliance. So we have similar requirements for structural, non-structural, and different actions which are ductility control, brittle elements, different limits. So all of these work has been done by a huge body of researchers, and those recommendations have come up. But again, these are recommendations, and actually we have found, because we work a lot with peer reviewers in US and with our colleagues in Philippines and other countries, that these are subject to discussion. These are not rules like the codes, because these are not codes, these are guidelines. So you can always kind of challenge them, you can always look at them, you can always do a testing to say, okay, no, this doesn't make sense. Or you can review, you can discuss with the peer review and or change the limits. So it happens many times that you can actually change these limits for particular projects. So that's the whole objective. So how PBD should work? PBD works by collaboration, starting from the architects, starting from the owner. They have to agree that we want to do it, because they have to pay more for the professionals. And I know getting fee from sometimes is clear, then it's easy. So the client will engage the architects. They will also engage an engineer of record. They will also engage a PBD consultant. They will engage a site-specific seismic study or tunnel or wind tunnel consultant, and they will also engage a peer reviewer. So there is a lot of consultants, a lot of people that need to be engaged for a successful, reliable, performance-based design to be carried out that can meet the objective that it's supposed to meet. So that brings me to the end of the first topic on the performance-based design and how that works. And second two topics that I don't think I have time. No, I don't. Second, you don't have time. Which is the value engineering and the peer review. I will continue with those in my next presentation, which I still have the luxury of having 4 more presentations, so I can keep continuing with that. All right. Thank you so much.